Hi everyone, today we're going to be covering topic 6.7, bond enthalpies. So put simply, the bond enthalpy is essentially the enthalpy, or in other words, energy, associated with breaking 1 mole of a particular bond. And this is very important that it's a particular bond, not a substance, in a gaseous substance. And so let's look at this example here. If you have Cl2, that can break apart into 2 Cl individual atoms, right? And they'll have that 1 extra electron because they're sharing the electron on their bond. And that energy, that delta H there, that's essentially the bond enthalpy. You have the same thing for something like CH4. That would break apart into carbon plus 4 hydrogens. And again, that has an associated delta H with it. And so there's a few common themes among bond enthalpies that we always need to remember. One is that the bond enthalpy is always positive because it requires energy to break a bond. And so delta H will always be positive in this case when we're thinking of bond enthalpies. And so this reaction right here of molecule AB going to A dot, or just the molecular fragment, and B dot. So just breaking that bond in half. We're not talking about ionizing. We're talking about just breaking the bond directly in half and each of those electrons going back to where they started. 2, energy is always released when bonds form. Or in other words, in this case, delta H is negative. So if we have an equation where we have A dot plus B dot, so the exact reverse of what I'm showing at the bottom, come together to make A bonded to B, delta H will be negative. This always releases energy. And 3, the greater the bond enthalpy, the stronger the bond. In other words, it is harder to break. So harder to break bonds have really high bond enthalpies. Now here's just a table of average bond enthalpies. You don't have to remember any of these. I just wanted to kind of show you what was going on here. But for example, if you have something like a CH bond versus a CC bond, right, this has a higher enthalpy, and so it's going to be harder to break, for example, than a carbon-carbon bond. And so on any question on the AP exam, or any of my exams, you're always going to be given a table, or at least going to be given the bond enthalpies for a particular problem, so you don't need to remember them, but you do need to remember that higher bond enthalpies mean that it's harder to break those bonds. Now, using these bond enthalpies, you can also calculate the enthalpy of a reaction. So we've done this previously, looking at enthalpies of formation, and we'll look a little bit more at that in the next lecture. But using bond enthalpies, the enthalpy of any reaction is always going to be equal to the sum of delta H of bonds broken minus the sum of delta H of bonds formed. I'll put these each in their own parentheses. And so, for example, if I had a reaction such as H2O breaks apart to form H2 plus O2 gas, in this case, my bonds broken are, if I look at the kind of Lewis structure here, I have HOH, H-H plus O double bond O. I break these bonds and I form these bonds here. And so for my delta H of reaction, I would take the bonds broken minus bonds formed. And so your kind of stepwise thing here is 1, you want to draw the Lewis structure. And if you are not up to par with drawing Lewis structures, don't really remember from honors chemistry, then always, you can come to me and we can have a conversation and I can give you some practice. Or you can go look up some practice as well on drawing Lewis structures, but we do need to know how to at least draw those so we know which bonds are broken. So first draw the Lewis structures, and then 2, you always do broken minus formed. I did just want to spend the time to do a very, very quick Lewis structure refresher just in case. And if after this you still need more help, then of course come find me. But if we have something like CH4, for example, the first thing we want to do is just draw out the dot diagram for carbon, which is shown right here. And also consider the dot diagram for hydrogen. And we can see here that each of these has one, or at least the one valence electron of hydrogen can bond with one of the electrons of carbon, and we can do that all around. And so if we're going to draw out this Lewis structure, we'd have carbon in the middle, hydrogen, 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 and hydrogen. And then there's going to be no extra electrons around carbon because all of them are in bonds. The thing you always want to remember, of course, is that you want 8 valence electrons per atom, except hydrogen, of course. Same thing over here for CCl4, right? Carbon has its 4 valence, chlorine has 7. You can form a bond right there, and we can do the same for all of them. And so that Lewis structure would essentially look like this. And then we must remember those electrons don't go away. Finally, if you have something like N2, right, nitrogen has 3 electrons that are unbonded, and each of those can form a bond with the respective nitrogen as such. This is just kind of a depiction of that. And so we would get N triple bond end. And if you see all of these, each of these should also have 8 valence electrons each. These are just a few examples, but you should be at least comfortable with drawing these Lewis structures out because it will be very helpful and necessary when we're thinking about bond enthalpies. And I'll show you in the next slide why that's necessary. And so let's take this example here where we have the reaction of O2 going to 2 oxygen. We're given a table of bond enthalpies over here to the right. And we're told to figure out the enthalpy of dissociation of O2, or in other words, delta H of the reaction. We've got to remember that the equation here is the sum of delta H of what's broken minus the sum of delta H of what is formed. And so in this case, we also need to think about our Lewis structures so we can see what's broken and what is formed. So if we look here, O2, the Lewis structure for that is O double bond O with 2 lone pairs on each of them. And so what we're going to be using for that is this right here. We're not going to be using that O single bond O because that's not the bond that we're breaking. We're breaking an O double bond. And then for 2O, of course, that doesn't have a bond there, and so we're not even going to use this bond type at all because that's not the type of bond we have. And so our delta H of the reaction is equal to the sum of bonds broken. Here, I'll have for bonds broken, I just have 495 kilojoules per mole. And if I look here, that's the only bond that I have. If I look here, I make 2 O, and there's no bond in O, and so this will just be 0 kilojoules per mole. And so my answer here will just equal positive 495 kilojoules per mole. Or in other words, this reaction would require 495 kilojoules of energy to break that OO double bond.